Hello, everyone. So today we're going to be talking about chemical fires. So we're going to start by talking about a incident that happened in 2005 at the Ohio State University's labs, where they had a organic lab where they had shelves just stock full of chemical solvents. And this is an indication of how it's not just the chemicals you need to be aware of, but where they're placed as well. Because one entire shelf ended up collapsing and falling down. Where this was particularly problematic is that this shelf contained bottles full of hexanes, which then shattered, releasing hexanes into the atmosphere where they were then able to ignite. So today we're going to be talking about, well, what sort of issues you may end up having when your flammable solvents get loose. So when doing this, one of the things we want to go ahead and revisit is that old elementary classic, the fire triangle. So this is the idea that any fire needs three major things in order to occur. The first of which is going to be the fuel. In this case, it's probably something like hexane, something preferably carbon rich, high energy, wants to break apart. Then we have oxygen. So this is most often oxygen, but in truth, it can be any oxidizing agent. So this can include any oxygen rich species, though this might impede the ability for fire to conduct. And in fact, most of the best flammable agents bring along their own oxidizing agent, whether this might be something like nitrate or maybe something a little bit more exotic. And then the third thing we need is heat. Now, in truth, heat can really be anything that helps the reaction get over that original activation barrier. Because once the reaction starts, as long as I keep enough fuel and enough oxidant, the reactions tend to generate enough heat to maintain the reaction and keep it going. So, in a more chemical perspective, what we're looking at is trying to separate any of our fuels, any of our oxidants, and essentially anything that provides the system enough energy to get over that original activation barrier. Now, this can actually be slightly problematic in nature, especially as we start moving towards more exotic fuels and more exotic oxidants. So, one of the other important things to worth noting is that because a reaction requires both fuel and, and an oxidant, most chemical reactions, if say I have propane or hexane sitting in a container, don't actually occur in the liquid phase. So we might think about a lot of our fuels catching fire, the reaction will never occur here in the main liquid body. Instead, it will either occur at or near the surface, where I tend to have some sort of evaporating fuel interacting with oxygen. So what I'm looking for is where we can have the most interaction in between these two. So this means that one of the classic ways you can try and reduce the likelihood of a chemical reaction from occurring is to minimize the amount of fuel that's able to enter the gas phase, or alternatively, limit the ability of oxygen to reach the surface of any flammable material. Once you do that, once the two species come in contact, as long as they have enough energy to overcome this original barrier, they're going to start expelling products. Now, if you're lucky, this might be able to suffocate your fire in and of itself. Unfortunately, due to the fact that we're generating a lot of heat, this will not only keep the reaction running, it tends to cause any byproducts to rise, bringing in fresh oxygen. So let's go ahead and look at some of the more technical aspects of flammability. So what we're going to want to do is try and be able to assess the likelihood that a chemical species is able to catch fire. And again, the biggest thing I want to emphasize is that except for notable circumstances, such as maybe some solid combustants where oxygen is able to enter the system, most fires are actually going to occur, or at least initially start with the chemical vapors. However, worth noting, once a chemical vapor catches fire, the heat will usually encourage more vaporization and thus runaway systems. So a useful thing to look at is once I know that the chemical vapors are what's catching fire, what I can do is look at what's called the flammability limits. And this is the idea that any material has a lower limit and an upper limit at which it can catch fire. So in this case, this is going to be in a percent volume basis. So if I have a sample of hydrogen, it's only going to catch fire if hydrogen is somewhere between 4 and 74% of whatever atmosphere is present. And it makes sense that if I'm below this lower limit, really what I have is a fire that is fuel limited. So I may get an initial, say, reaction of a benzene molecule and with the surrounding oxygen. But if I don't have enough benzene, then the energy produced from this reaction essentially won't cascade and cause other molecules to catch fire. Alternatively, if I say have more than 7% benzene in my atmosphere, this essentially tends to mean that the oxygen is now the limiting reagent because my benzene has displaced oxygen from the atmosphere. And so I don't have enough oxygen to keep the reaction going. And so thus we tend to have these upper and lower limits for flammability. It is worth noting that all of these upper and lower limits tend to assume exposure to the atmosphere. If you're working in an environment that has more oxygen present, for example, you're working with plant samples that are oxygen enriching your environment or near an oxygen tank, this number can be much higher. Alternatively, you may have another form of oxidant present, such as a nitrate containing species. So again, this ends up providing a good general rule and something to keep in mind when you're thinking about will something catch fire. Sometimes if you're going to be forced with a species like say methane, ethane, or propane that are going to be in an atmosphere, one of the things you can do is instead try and close off the atmosphere to limit any entrance of oxygen and thus make sure that your whatever gas you're working with is above the upper limit. And again, it's worth noting that these are generally considered the concentrations at which any chemical vapor can catch fire in the air. Again, circumstances can be used to change these numbers. And again, if I'm above this threshold, I don't have enough oxygen. And if I'm below this threshold, I essentially don't have any fuel. So I have provided a series of flammability limits available for you on Blackboard in case you're interested in working with other materials or wanting to know under what conditions you may end up having to watch out for a chemical species to catch fire. However, again, one of the important things to know is that ratios of fuel to oxygen aren't going to be the only thing that can control a fire. Because it turns out that I'm going to need a certain air temperature in order for the reaction to produce enough heat to maintain essentially flammable conditions. So it turns out that every chemical species is going to have some temperature below which it won't catch fire. And it's worth noting that in this case, we're tending to talk about the pure liquid species when we're referring to the flashpoint. So it can be worth noting that one of the ways in which low temperatures can limit the likelihood of chemical ignition is simply by reducing the amount of vapor that's in the gas phase, more or less by impeding evaporation. So again, once we have our flashpoint, we can use these to evaluate at what temperatures a material can or cannot catch fire. And so, for example, I can go ahead and use this to evaluate, say, the flammability of acetone. So if I have a container of acetone, even if I take a match to it, if I'm below 0 degrees Fahrenheit, so if I'm not just in a freezer, but in a very cold freezer, you can actually prevent ignition. However, one of the things that's worth noting is you can also use this for uh, for other uh, notations, which is the idea of you can actually understand diesel and gasoline engines simply by looking at their flash points. So it turns out that if I have a diesel engine, a diesel engine tends to operate by more or less compressing the diesel so that the flash point uh, lowers to the point that at ambient temperature, the diesel can catch fire. Because again, note that these flash points are just for a 1 atmosphere or essentially boiling chemical liquid. In comparison, if I have gasoline, it's able to ignite at much lower temperatures. So this is more or less the reason why if you're working in, say, Alaska, you often need to put an electric heater on your diesel engine to make sure that your diesel can actually ignite. Whereas only on a very cold day will you ever have to worry about gasoline being below its flash point. Again, one of the things that you should watch out for is that if I have a fire that occurs very quickly and it's in an enclosed space, this is pretty much the definition of an explosion, because fires do end up tending to produce um, uh, when they produce CO2 and O2, this can cause the pressure of the container to rise drastically. And so if you don't leave a place for these vapors to go, this is more or less what we're talking about when we're referencing the ideas of explosions. And again, one of the things that is worth noting, if a material is above its flash point, you are going to want to make sure that the material is kept away from any ignition source. So this is anything that can provide that extra little bit of energy to get the system over its activation barrier. So the classic ignition sources are open flame, an electrical line, or just static electricity, because all three of these can add enough chemical energy that once you're over the ignition point, if you're above this flash point temperature, fires will result. However, it turns out that these aren't the only major ignition sources. One final important ignition source you have to watch out for is just temperature itself. Because it turns out that if I heat a sample up high enough, that the ambient temperature of the room can actually provide enough energy for the system to overcome its initial activation barrier and the reaction to become, well, let's just call it runaway. Because it turns out that spontaneous combustion is a thing. It just happens to be that you need to get to high temperatures for it to happen. So for example, some of you may be aware that if you get paper up above 451 degrees Fahrenheit, yes, I'm talking about books here, paper can go ahead and auto-ignite and more or less spontaneously combust. Whereas something similar can happen if you essentially get leather to more than twice the boiling point of water. So again, not exactly something easy to happen, but leather can indeed spontaneously combust as well. However, it turns out that some materials were actually quite used to this happening. So whereas you know that diesel has a higher flash point temp, it turns out that it has a lower auto ignition temperature. So this is the reason why why a diesel engine can work by more or less just compressing diesel, increasing the pressure of the diesel system until the auto ignition temperature lowers to essentially room temperature and it will auto ignite. Thus, a diesel engine doesn't need a spark plug a gasoline engine does, just because it has a slightly higher auto ignition temp. One of the things that you should watch out for is that some chemicals can spontaneously ignite through the air. This is a little bit less through a flammability reaction and more of a chemical reaction. So we'll talk a little bit more about that next time. And again, as a reminder, it turns out as long as you have a high enough exposure to oxidants, plenty of other solids are flammable as well, though it is not uncommon for this flammability mostly being due to the fact that a lot of solids will contain some degree of oxidants in and of themselves. So that brings us to the end of flammability and fire. Next time, let's talk about some of these alternative methods for disastrous things. Till then, take care.